Welcome back. Let's get a little bit more into the performance technology used in modern day vehicles compared to what it was, say, 40 years ago. Recent videos have come up talking about the knurling on pistons uh, and the surface roughness of the cylinder bores or the pistons themselves. Now, there was multiple practices by individuals that were tinkering with pistons back in the day that would either knurl the pistons to reduce the frictional surface area of the piston to make contact with the cylinder walls. More modern day oil geeks will come out and say that the texture of the cylinder walls is more advantageous to carry the oil to be able to lubricate between the piston and the cylinder wall. Now, again, if you need a little reference to what some of the newer oil techniques or practices are out there, a previous video that I posted pertaining to cylinder wall clearance might help you out. So if you're not familiar with that, go ahead and watch that video first before reviewing this one, because with the thinner viscosity oils, they're not there to carry the components necessarily. They're more for the cleaning and cooling aspect, where engines designed over the years for almost 100 years used oils for a lubricant, not necessarily for a cleaning or a cooling aspect. That was left up to the engine's coolant, whether it be through glycogen-based coolants or air-cooled engines. The oil was there to lubricate, not necessarily to cool the engines. So again, some of the practice that were occurring during the late 1960s, early 1970s with Smoky unit, a lot of them were to address friction to reduce the amount of oil that was also being carried along with the piston. The liquid of oil is actually heavier than the piston. So if the pistons are soaked with oil and cannot shed the oil off, they are increasing with weight, and they also become inconsistent. So everybody understands that when you are trying to build a high RPM engine, you want the crank and the rotating assembly to be balanced. But once you start throwing oil at all the components within the RPM range, if the oil is thicker or heavier, it will cause an imbalance through the entire system. Now, obviously, the harmonics that are relayed into the components, into the rotating mass as it's spinning, can be dampened somewhat through the dampener or through the driveline component, whether it's a clutch or a automatic transmission. But the balance of the rotating assembly still comes down to how much each component weighs. You're going to see individuals going out there and weighing each individual component, whether it's a piston or piston rings, to make sure they all weigh the same, and removing either material from the aluminum or steel components that they're constructed out of to get you in a general ballpark to get everything balanced. The crank will go through a different process within a spinning device to monitor where the heavy spots are within the crank, to remove material or add material here, to balance the crank separately. The bob weights that mimic the weight of the actual connecting rod and piston are clamped onto that. You'll notice that those weights are not orientated all in the same direction. Okay, so the rotating mass cannot necessarily find a true zero balance. If you need me to prove you wrong, let's take something a little bit more simple that has less moving components. Let's take a wheel and tire, for example. If you get a brand new set of rubbers put on your vehicle, and you take it to the tire shop and get the tires mounted on your car, they're going to put on a balancer, and they're going to have you the clamp on or sticky weights to be able to balance the rotating mass of the tire and the rim to zero it out. Now, as you drive it, or if you pick up stones along the roadway, that is throwing off the balance of your tire. At what point do you start to feel vibration or wobbling within your tires from any debris or wear and tear of the tires? Because once again, if vehicles are not maintained, say the alignment is off, they might wear off the rubber a little bit more on the outside or inside the tires. If they're running with low or high air pressure tire or air tire pressure, Either the outside of the tread or the inside is going to wear out, changing the balance of the tires. Now, some of you, every other oil change, your technicians or your shops where you might take it in, they will recommend that every other oil change that you have your tires rotated and balanced, because all four tires wear at a different amount and they can go out of balance fairly quickly. So by removing the clip-on or stick-on weights, you can rebalance the tires to allow them to perform better. Same thing happens in a rotating assembly of an engine. With the oil sloshing around and the different concussion from each ignition cycle, it causes the balance of an engine to be imbalanced. Okay? So the big discussion right now is between a flat crank type design with the new LT5 engines from General Motors to the older design. The flat crank design connects basically four cylinders in the same balance, where the other bank or the other four cylinders are connected together and they feed off each other. While one is receiving compression, the other one's on the exhaust stroke. The exhaust gas is actually being compressed or pushed out of the exhaust, actually becomes a cushion for the ignition of the opposite cylinder. And it's directly related from one side of the engine or within the firing order. It helps balance the rotating assembly. But in the crankcase area, as oil is being thrown around, even with modern day engines that have direct oil squirters squirting oil to the bottom of the pistons, that is there for the cooling effect. It is not necessarily there for lubricating. Okay? Now, with all the additional applications of piston skirt coatings to different cylinder wall material, whether it be cast iron or steel sleeves, the crosshatch has also changed throughout the years. When cast iron piston rings were utilized, in order to have enough abrasive to wear the cylinder walls in to match the piston rings, a very strong 30-degree crosshatch in the cylinder walls needed to be there for the finer finish of the piston rings. So they would wear together. Approximately after about 5,000 to 10,000 miles, the rings would seat into their position. Now, during that time, piston rings are rotating around the pistons. The skirts of the pistons only make contact with the cylinder basically in two locations. Where there is actually tilt to the piston as it is being exposed to the compression or exhaust strokes within the engine. So today we're going to get over the actual design of pistons, the types of piston connection points that were practiced 40 years ago compared to nowadays, and how the cylinder wall finish is not as important as what some of the oil geeks are promoting out there. Okay, you can have chromed cylinder walls, perfectly smooth with absolutely zero crosshatch. They will still seal the exact same with modern day pistons, high tensile steel pistons, not cast iron, with thinner profiles, because the oil is also lighter. So it will be able to be scraped away from the surface much more efficiently than the older, stickier, high viscosity oils. Now, another thing that has occurred over the last 40 to 50 years of piston pin, not the location, but piston pin offset, or excuse me, not piston pin offset, piston pin design is going from the pressed pin, okay? Normally, 40 years ago, in order to attach a piston to the connecting rod, the pin was permanently secured to the connecting rod. Obviously, by heating up the small end of the connecting rod, expanding enough to be able to put the piston pin in while it's also being driven through the piston itself, when it cooled, the connecting rod would squeeze around that pin. And as the connecting rod would be swinging on its pendulum, the actual pin would be rotating at the same rate as the angle of the connecting rod. During the 1980s, they figured that it was a little bit more efficient for machine shops or your do-it-yourselfer to be able to change pistons by not having a heat connected pin. Floating pins then made its way into the industry. In order to locate and keep those pins centrally located within a piston, they used either C-clips, E-clips, or rings to be able, within the pistons, to secure the pin from moving left or right. Now, in that process, as the connecting rod is swinging on its pendulum, it now gives it three surfaces that can lubricate and allow that pin to actually rotate 100 or 360 degrees all the way around the position of the pin in its location, reducing the amount of friction being expressed into the piston for rocking inside of the cylinders. So even with older technology like Smoky unit and knurling of the pistons, two-stroke engine builders have been doing similar things like that for decades. Now, the skirts of the pistons are normally drilled. Instead of just having a knurl across the skirt of the material, causing high points that would naturally wear down because the aluminum is softer than the actual cylinder wall itself, and with the more aggressive crosshatch that was in the steel of the cylinder walls, it would remove those high points in a fraction amount of time. Within the first 20 minutes of braking time, those high points would be gone. But the gaps created by the knurling in the piston would also create a larger gap for oil to ride in as the piston was going up and down, helping to lubricate. Two-stroke engines would actually drill holes all the way through the skirt of the material to lighten the piston itself and to allow oil to escape both from between the piston and cylinder wall clearance to actually supplying oil through the inside of the piston outwards. Because once again, most of your oil that's being sloshed around, as the piston is traveling down in the cylinder, the piston rings are scraping the oil off of the cylinder wall. As it goes up, there is nothing supplying oil to the cylinder wall until the crank is throwing the oil either onto the cylinder wall or having a direct lube oil squirter supplying the oil to the bottom of the piston. Now, again, if we look at the bottom design of most of the pistons, now both of these designs do not have the connecting rod installed. So what you're seeing is basically how the pistons have allowed to be shaved away to reduce weight in a couple different ways. First of all, they're removing aluminum material from the actual piston. Now, aluminum, in order to remove weight, you have to move an excess amount in order to actually see a weight savings gain. But by narrowing the piston pins, which are actually made out of steel, a small portion removed from those pin lengths or diameter or wall construction can reduce the weight of the piston end or small end of the connecting rod tremendously. Okay, so in order to reduce the amount of friction that's actually being caused between the connecting rod, the pin, and the piston itself, they've gone to floating pins, and they've also narrowed the pin to make it smaller. They've also gone to a different contoured piston wall to where only the regions on the exterior of the pin that like to do most of the flexing, the actual areas within the piston itself or underneath the piston itself, not the connecting rod end, are lightened with a narrower wall and a reinforced end. So if you were to take one of those piston pins and cut them in half, you would actually see the wall of the pin is actually contoured, where the reinforcement comes from the surrounding area on the very end, and then the areas that are shared with the mating material of the piston itself, the plateaus, is shared with a very thin area of the pin. So the load being forced on the piston and to the connecting rod through the connection point is being shared over a wider area. So they can reduce the width of the wall, or excuse me, the thickness of the wall of the pin, reducing tremendous amount of weight from the piston end of the connecting rods by going both narrower and having a different profile. With them also being floating pins, they are able to rotate within every revolution that the piston is starting to tilt or the pendulum of the rod is rocking back and forth. Now, typically under the compression stroke, okay, the ignition pushing the piston down causes enough friction on the piston and shared through the connecting pin is that when it's rotating down and the pendulum of the arm is following the crank around, the piston will stay in one location. But as it's being relieved, as pressure in the cylinder is being relieved, either because of the growing area or the exhaust valve opening, the piston now is relieving that pressure when the pendulum of the connecting rod is rotating. So for every rotation of the crankshaft, it is actually spinning the pin a small amount each and every time, allowing the pin to be exposed to either oil, fresh oil, or to oil delivery holes that might exist in between the bottom of the piston and the pin, or through the top underneath the piston in order to allow that oil to drain down on top of it, helping it lubricate the actual piston pin. Now, all of that was done with two-stroke engines way back in the day. I can remember in the late 1970s, early 1980s, where motocross, most of your professional motocross engine builders, they were utilizing pistons that first had a restrictor. So it didn't allow the actual piston ring to spin inside of the piston itself. And that groove, that piston groove restriction was not removed, so that it did not have a groove all the way around the piston. That was always the side of the piston that located over the intake port. So as the piston was going down, the piston rings did not interfere with the actual intake port itself, with the sharper edges for that ring to be hung up on or start to shear away the edges. But they were still able to hold combustion chamber pressures without having a lot of blow-by. Because once again, any engine that has blow-by from the combustion side into the crankcase is not something that's very efficient. It's a loss of power. Two-stroke engines also use the oil that's in their crankcase to be part of the ignition cycle. Okay, so again, the fuel, there is no oil alone by itself in a two-stroke engine. It is actually the oil and fuel mix that does the lubricating. So now going back to what I said previously about these oil geeks, okay? Yes, you guys know what I'm talking about with the lake speed and all the different oil technologies coming out there with, different synthetics and cross-hatching finishes. Two-stroke engines were way ahead of its time because the oil did the lubricating. Your actual two-stroke and fuel additive is the oil for the lubrication. The petroleum fuel was there to actually clean, the crankcase area and to cool it, along with supplying the fuel to be ignited to create power within the combustion chamber. Okay, so all of this oil technology out there, once again, folks, when I've gone back and talked about the compression protection created by thicker oil viscosity oils, that's within a four-stroke engine. Something that's, the oil's only there for lubrication. It's not there necessarily for cooling or cleaning. Cleaning additives have been added to the oil with more modern day synthetic oils, so on and so forth, to help keep it clean, because oil, when it gets hot, the carbon deposits are left behind and it will coat the components throughout the entire engine that it's exposed to. If it does seep by the piston rings and get to the combustion chamber, the thickness of the oil will not ignite as efficiently as the new modern day lower viscosity engine oils. Okay, so the technology that's out there with that is not true. It's something that's been adaptive already from engines of yesteryear. In motocross engines, once again, I told you that they would drill holes through the pistons, typically through the frictional areas of the skirt because of the tilting of the piston. With race two-stroke engines, they were some of the first platforms that used the floating piston pin, reducing the amount of friction that caused the piston to rock back in the cylinder back and forth to create that friction. So while some of the performance modifications done to pistons were to address the old technique of heat grabbing piston pins, okay, where they would stay connected to the connecting rod and turn only within the circumference of the pendulum of the connecting rod. That friction caused the pistons to shovel one way or the other, causing more friction on the skirts. So to reduce the friction, they would drill holes, reduce the amount of material there to actually cause the friction. Those holes also allowed more oil to be exposed to different areas of the piston, especially around the piston skirts, to reduce friction. Once they went to floating pins, the pistons lasted longer and actually had less friction being forced in between the piston and the cylinder walls. So the need of those holes in the skirts of the pistons were no longer needed for the lubrication. They were only being drilled out for lightening the actual piston. Now for the last 20 years, let's even go back sooner than that, from 1985 on, the Pro Stock drag racing and NASCAR high elite racing, they figured out a long time ago how to design a piston, reduce the width of the pin, and the way that they actually constructed the piston is creating more with webs. So when we go back to the piston pin wall configuration of the areas that actually needed the reinforcement to where areas that are shared over a larger area can be a thinner material, it's reducing heat, or excuse me, reducing weight, not heat. With that in account, they've also been able to design pistons with that same mentality. They can remove material from all different locations, but they'll keep the ribbing. No different than your chest cavity, your ribs. They're not a solid platform. The ribs are able to flex a little bit and move with each breath. The ribs inside of a piston, if they're designed like this, again, if you notice the ribs of the more modern day pistons, everything's been shrunk towards the center. Again, because of the more narrow floating piston pins. They're also only adding those ribs to the frictional sides of the piston. They're not adding them to the sides of the pistons. Okay? Now, if you tune into Morris Race Engines, Steve Morris Race Engines, and you go back and look at his multiple videos of what he's been doing with his SMX series engine, so on and so forth, he has gone to the point where he's going back to the old technology, where he's going to the full width piston pin. And on the ends of those piston pins, instead of allowing either a E-clip or C-clip or a ring to retain the center of the piston pin from floating in there, they're retained with actual caps. And those caps are restricted from moving from the actual oil control rings. So the top of those caps actually create a portion of the oil control ring gap. So as the piston is rocking back and forth on the piston pin, the caps do not move. Okay, so if we go back to technology once again, we learned in the 1970s that a pressed pin connection point cause the pin to constantly move in the same direction as the pendulum of the connecting rod. In the early 1980s, within two-stroke motocross racing, they found that to reduce the friction and allow that pin to spin, sharing the stress and the life expectancy of the pin, is to go to a floating pin. It also reduced the rock that was initiated into the piston in the cylinder bores themselves. Following along? Now Steve is going back to the point where, yes, he's using a floating pin, but he's using caps to retain the pin in its center location. In between those caps and the pin ends is additional frictional area. It's closing off the end of the pins to receive any kind of oiling. He's also going to a wider piston pin. Again, going away from the old technology to the new, he's actually going back to a semi-between to where the pressure above the piston is being shared more equally around. He's getting more of a more stable transition from the compression pressures through the connecting rod. The reason why he's doing that is because the connecting rods he's using are aluminum. Again, aluminum, in order to reduce its weight, you have to relieve it of a lot of material. So in order to have the strength that Steve Morris that requires from his 5 and 6 second door slammers, he has to go to a very wide connecting rod. So in order to use piston pins, he's had to go to a wider area of where the piston pins are in. But the area of the piston pin and the exterior of the piston has been widened, but the actual ends of the piston or the pins have been narrowed. There's a wider area of the actual connecting rod. This area here. Reducing the amount of flex that's being exposed to a piston pin, period. More of the connecting rod is taking up that space. Now again, as I stated before, if you want to run really fast and break down, make sure you're taking Steve Morris's advice. You will go fast. It's going to cost you a lot of money because you're going to be breaking stuff. Again, you go back about a year ago when Steve Morris tried out a new set of connecting rods. Every single one of them, not just one twisted and broke off from high, tensile strength. All 8 connecting rods sheared off on the small end of the connecting rods. Why was there stress being added to this portion to where it literally caused the metallurgy of those connecting rods to shatter? It's aluminum, folks, okay? Aluminum can actually withstand more of an impact than what steel does. Okay, steel is going to stretch a little bit, but from impact, aluminum is actually harder. It will stretch from heat or being pulled on, it will stretch, but it will not compress. It's actually stronger on compression than what a steel connecting rod is. So why would you have connecting rods snap off on the small end? Because there's so much friction happening between the small end and the floating piston pin with the pendulum and the forces above the piston pushing down, not allowing that piston pin to spin. It's causing, when the pendulum is at this way, approaching top dead center, increasing the pressure from turbo and ignition process, turning, which anybody, real quick, I'm going to give a prop here. Okay, everybody realizes what this is, right? Baseball bat. When you go to swing, okay, for you baseball players out there, you understand, if your hands are twisted to where your fingers are pointing in the opposite direction and you go to swing, one of your hands has to turn in order to keep your line or your fingers in line. Or if you're a golfer out there, you'll recognize this hold, keeping it straight. Okay, when you're applying pressure or swinging the bat, the alignment of your knuckles have to be straight up and down with and in parallel to the actual plane that you're swinging the bat through to make connection with the ball. During that time, your hands are creating friction and your wrists are flexing. Okay? Just like the pendulum of the connecting rod in the engine, if there's a restriction or friction of the piston pin, it's forcing the wrist to flex. So Steve Morris SMX engine and his connecting rod floating piston pin design with the caps on the end actually match the same kind of friction caused by the old pressed pin design, causing more stress to be transferred onto the connecting rod and snap them, all 8 of them, right here. So again, different technology from different people during different eras, from Smoky Unique through the progress of more modern day motocross two-stroke engines, to your oil geeks, to YouTube content creators talking about all these new different designs or copying things from old legends. We have moved on to them. We have advanced in technology and understanding. While some individuals are going back to the way the things used to be, and they're finding problems. Okay, I'm going to close the video out with this real quick because I know you guys are just saying, oh, I'm just bashing everybody and I don't have proof to go that fast and so on and so forth. That's fine and dandy. But again, as somebody that built engines for customers, I was held liable for those engines if they broke down with warranties. And if an engine came back within 1 year and it was either the failure of a part or from the actual assembly of the engine, guess who got stuck with the entire new build? Right here, folks. So when I talk about building engines that actually have to survive, I know the modifications that can be done to engines or the different ways of technology have transferred throughout the years to make engines more reliable. Because once again, I don't want anybody going out there and building an engine that only lasts 10,000 miles and you're only taking advantage of the top 2,000 RPM of the RPM range in order to get the satisfaction out of it. Because majority of you, 99% of you, are either idling around town or going stoplight to stoplight if you live in a city type environment, or you might be cruising down the road at say 25 to 3,000 RPM. The amount of time you spend in that 5,000 to 7,000 RPM range is going to be advantageous to all the information you're getting with all these dyno sessions and dyno mules and so on and so forth. But it's not giving you the real picture. Engines that are being operated at 7,000 RPM taken to extreme measures, like the 360 or 410 sprint engines that are going for 80 grand. There's a reason why they're charging you 80 grand for those engines, because when you bring it back, they have to freshen up those engines and replace the parts over and over and over and over again. Because they're not actually putting the parts into the engine that are designed to allow them to last. It's no different than you Snap-on tool buyers. You're paying a higher cost because you will be replacing that tool with normal use over and over and over again. So what would you rather have, the expensive tool that you're going to have to replace multiple different times when it comes to building an engine? Or do you want to construct an engine that will last, provide you the most amount of enjoyment for every dollar you spend? Or go to the track, be the fastest one weekend, and the next weekend you're oiling down the track? What kind of street credibility is that going to bring you? What kind of enjoyment are you going to get for every dollar that you spend? YouTube content creators that are giving you all this information, go back and do the research. Look at how things were done in the past and learn from their mistakes. Again, when pressed pins were used, Smoky Unique seen an advantage to the neural pistons. But approximately 10 years after that, the industry of two-stroke engines showed the way to get away from that. That we didn't need it anymore. And technology has advanced that much further from the piston manufacturers. Depending on which manufacturer you choose, if you're replacing your pistons, whether it be with a cast iron stock replacement type piston utilizing a press pin, or going to somebody like JE or Wisco or Mall that has already gone to floating pins, and the pin technology is actually going to be like this here. They've done half of the work to reduce the weight, provide you with a better component than as if you're using a piston from its original source. So with the exact same compression ratio, exact same components through the entire rest of the engine, just the modifications in the pistons are going to be noticeable in the seat of the pants. So yes, utilizing older pistons, if necessary, you can reuse them. But the benefits of newer pistons is well worth the additional $600 to $1,200 that you might have to spend for a forging or hypertonic type piston. It's going to be lighter, it's going to be stronger, and it's going to put less stress on the stock components of the engines. Now I'm going to have, sorry, I was going to shut the video down with that. We can't forget the actual other end of the connecting rods. So for those of you that are rebuilding with stock components, stock connecting rods, if you can identify if they're a performance variation, most of your Chryslers are. Some of your Chevys obviously went to all kinds of different other ones, whether it be powdered or pink rod, so on and so forth. You can upgrade them with the actual cap bolts. Now, if you look at ARP, which is probably one of the most popular replacement bolt manufacturer out there for connecting rods, they will show you 3 different variations they have for replacement with stock connecting rods. They'll have your stock replacement, they will have knurled, and they'll have wave lock. Okay, so let's draw a connecting rod bolt real quick. Now your stock connecting rod replacement bolts are going to be self-locating, that as they're being driven through the connecting rod end, not the cap, they're going to have a tapered shank to the bolt, allowing them to be centered into the actual opening. But there's area of the connecting rod that is not being supported by the actual connecting rod bolt. Okay, there's a gap because of the taper. By knurling it, it is growing the diameter of the bolt, okay, with high points, so that when it's driven into the connecting rod, it'll help centralize the bolt and reinforce the actual casting of the connecting rod. Wave locks, instead of using a knurling the whole entire length of the rod, or excuse me, of the bolt, you create a surface area. They're actually compressed. So after the bolt has been forged, before it has been completely cooled down, they'll actually compress it from one end to the other, causing the metallurgy to separate and actually grow in certain areas, and you're going to get that wave lock design. Now again, that additional diameter to the bolt, when driven into the connecting rod, is going to help it keep it centralized, okay? And it's also going to reinforce the actual connecting rod itself. So when you hear individuals saying, I want to take a stock connecting rod, build it in this project, and I'm going to get an additional 150 to 200 horsepower more than what the factory ever intended the design to be, you can replace the stock connecting rod bolts with either knurled or wave locks, and it would increase the strength of the big end of the connecting rod. Okay? So even without changing the components, bolts can be purchased to modify the actual strength of your connecting rods. Now I'm going to ask you one question. If you're changing the pistons on your stock connecting rods and you're using a pressed design, you have to heat that small end of the connecting rod, once again, right, in order to make it increase in size, to be able to press the pin out, hopefully fast enough that you can take the new pistons, put them over there, and reinsert a piston pin And as it cools, it'll shrink down around the pin again. What happens to cast iron when you heat it? And when you let it cool to regular room temperature without a forging quench, it becomes brittle. So individuals that go out there and get higher dome pistons, which usually and typically weigh more than the factory flat tops, they change them out by simply heating the rod, the small end of the rod, pressing in and out the pin, and letting it cool at room temperature. The heavier piston, the increased pressures above the piston on a high compression engine, and typically the higher RPM of that engine, you're going to find your weak spot in your reduced strength connecting rod at the short end. You're either going to twist or snap it. Okay? So all of the configurations in connecting rod technology today, whether it be I-beam, H-beam, to piston pin width, piston pin wall construction, and how it's being lubricated, and whether or not it's turning with every motion of the pendulum of the connecting rod, will lead you to the actual most benefit that you can have within modern technology. You can get pistons with a floating pin to replace the high performance or stock components that you have that are pressed, and you'll gain more power, reduce friction, and reliability without having to lose the strength of your connecting rod. By the amount that you increase by changing the connecting rod bolts to a harder material, chromoly, to either the knurled or the wave lock, you are strengthening the big end the same as you're reducing the amount of stress that's being placed on the small end with a floating pin and lighter construction. So hopefully that helps out. Again, this was topics that, yes, I basically seen Uncle Tony's Garage do with his live last night with Dr. Art. As I said, I only agree with some of the information that's being shared from Uncle Tony's Garage or any of these other YouTube creators that might be having, different editing to their videos, or Mopar Joe and Charles Salvadio and stuff, building stuff with old technology. They're leaving out the actual advantages of newer technology that doesn't necessarily cost anything more. But at the same point, you even have guys like Steve Morris, or even these $80 million or $80,000 sprint car engine builders of 360-410s that have to rebuild their engines every single weekend. They are not building reliable engines. At our previous shop, we could build engines that would make the exact same amount of horsepower, spin less RPM, have less modifications done to the intake systems because of class rules and restrictions or size of carburetors, and they would last a whole entire season. So do I need to necessarily show you proof of the stuff that I'm buying for high dollar? Or you can just go look and see the history of some of the racers from our region that we built engines for, that made it to the big leagues like NASCAR, NHRA, Top Fuel Dragster, or Pro Stock Racers. Those are the type of engines that we built. And these guys run the engines to the ragged edge. If they broke down, guess who got stuck with the bill? So yes, durability over peak horsepower any day. Because in the real world, it's the individuals that can finish the race, not just the ones that can complete one lap with the fast amount of time. Have a good one.